So in the last video, we talked about the range and limitations of this little 3-bit toy problem. Now we're going to do a couple of examples. Let's do 3.14. Let's see how good we can represent the number pi in this little 8-bit toy problem. And then let's take this middle one, or this bottom one here, and see what this corresponds to in terms of a 8-bit floating point number converted into base 10. So the first one we're going to do is 3.14. 3.14, and this is the number we're going to convert into base 2, an 8-bit base 2 representation. So what do we do? Well, first we got to figure out what the number represents. So 3 we know is 101, right? Is that right? No, that's not 3, that's 5. Look at me go. 3 is 0, 1, 1, right? 1 plus 2 is 3. You learn something on YouTube every day. Now the 0.14, we're going to have to actually go through our math and figure it out. So let's start over here, 0.14. And remember, we're going to multiply by, I'll make it bigger, 0.14. And we're going to multiply it by 2, and that's going to give us our first number. 0.14 times 2 is 0.28. Nothing in the ones column yet, so our first bit is 0. 0.28 times 2 is what? Well, 0.3 would be 6. So 0.28 would be, well, let's actually get our calculator going here. 0.28 times 2 is 0.56. Okay. Then 0.56 times 2 is probably 1.12, right? So multiply by 2 is 1.12. Then we have 0.12, because we keep that 1, times 2. 0.12 times 2 is 0.24. And we can keep going. We can keep going forever. We're going to get a smaller number. Eventually we might finish, but we'll see. 0.24 times 2, 48.48 times 2. 0.96. Now this one is probably going to give us a number that's bigger than 1. 0.96 times 2 is 1.92. And we can just keep going and keep going. But remember, our conversion, what we're converting into, really only has 4 bits of accuracy, depending on what we're doing. So that's probably enough. So our number, 3.14, is 11.00100001 and a bunch of other stuff. Okay, that's 3.14. We could do 3.1415 and see what happens. But that's 3.14. Now, we're going to try to convert this into our floating point representation. Step 1 is to normalize. We need to move that radix point so that we get 1 point something times 2 to the something. So this is 1.1001001 times 2 to the what? Well, we move that decimal point 1 space to the left, right? 1 times 2 is 2. 1.5 times 2 is 3. So we're multiplying it by some positive exponent of 2. In fact, 2 to the positive 1. Okay? So that's the number that we're representing. So now our mantissa is going to be just the first 4 bits. That's all we can represent. So our mantissa, our significand, is 1001. What's our exponent? Well, don't forget, the number that we represent minus the bias gives us the number that we want. So to get the number to represent, we start with the number that we want, which is positive 1, and we add the bias. So exponent is 1 plus the bias of 3, which is 4, which is 100. That's the exponent. The sign is 0, so it's positive. So the full representation is 0 for positive. Let's get that in here. Then we represent the exponent next, and then we represent the significand. Now, what number actually is that? Because we said we want to represent 3.14. But what number actually is that? I know it's not 3.14 because there's several bits of significand that we're not representing. So what actually is that? Let's see. Let's go backwards. Let's start with 0, 1, 0, 0, 1, 0, 0, 1. And let's see what that is. So first of all, we split it in pieces, right? 0 is sign, is positive. That's great. 1, 0, 0 is biased exponent, which means the exponent is that minus the bias. So 4 minus 3 is 1, which is what we expect. Then the significand is 1.1001. Don't forget to put that 1 point back in, which is 1 plus a half. 1 plus a half, there's no quarters, there's no eighths, a 16th. Which, if we look at our calculator, 1 plus 0.5 plus, let's see if I can do 1 divided by 16. I could have reciprocated it, but that's okay. Is 1.5625. Well, that's nothing near what we tried to do. But we forgot to multiply by the exponent. So we need to say times 2 to the 1. So we multiply by 2, and we get 3.125. Wow. We wanted to represent 3.14. The number we got was 3.125. So this is not the number we wanted. And what you'll find in your regular floating point numbers in your programming, that most of the time you get close to the number you want because you've got a lot more bits. 32 bits means you've got a lot more bits in the significand, a lot more bits in the exponent. So most of the time you get the number you want, especially for, human scale numbers. But sometimes you don't. Sometimes you get numbers that aren't exactly what you want, and bad things can happen, as we'll see. So that's just an example of how to convert from base 10 to base 2, and then from base 2 to back to base 10 to give you floating point numbers in our little toy problem. Next thing we'll do is we're going to look at this stuff in the context of now doing operations on floating point numbers. And then we'll look at this in terms of the full-scale floating point representation.